class, I explained about concept of columns. A column is a compression, take only compressive force, and we discussed about types of column: short column, medium column, long column, based on the values of L by D ratio as well as tenderness ratio. Then how the columns fail. So short columns fail by crushing, long columns fail by buckling or crippling, intermediate columns or medium columns, they fail either by crushing or by buckling. So those things we discussed, and end conditions, support conditions we discussed. What are the boundary conditions we had to use? So at a hinged end, you have deflection 0 but slope not equal to 0. At a fixed end, both deflection and slopes are 0. And at free end, both slope and deflection are not 0. So these are the boundary conditions we discussed. Then stability of columns, I told about stable equilibrium, unstable equilibrium, and neutral equilibrium. So if the load acting on the column is greater than the crippling load of the column, then it is it's unstable. If it is less than crippling load, it is stable. Then it is equal to crippling load, it is neutral equilibrium. So these three equilibrium conditions had explained. Now today we will derive important formula called Euler's formula. So Euler's crippling load or Euler's formula we are going to derive for different types of columns based on the end conditions. I told you that there are four types of columns we have in this chapter. Both ends hinged, both ends fixed, one end fixed, one end hinge, and one end fixed, one end free. So these are the four types of columns we have to deal with. So before going for the derivation of that Euler's formula, so that Euler's formula gives the value of crippling load. So that is the minimum load that a column can take before buckling takes place. That is the meaning of crippling load. So before the column fails, long column fails, so whatever load it can take, maybe 800 kilonewton or 1000 kilonewton, whatever load is there, before it just starts buckling, so that is called as the crippling load or buckling load. To find that load based on the end conditions of the column or support conditions of the column, we have to use that Euler's equation. So before going to derive the Euler's formula, we will discuss what are the assumptions we are going to make to derive that Euler's formula for long columns. So please note that Euler's formula is used only for long columns. In that case, L by D ratio is greater than 30, or tenderness ratio is greater than 120. So all those things I had explained yesterday. Assumptions. First assumption, the material of the column is homogeneous and isotropic. So just as in the case of beams, so all the properties, physical properties are same in all the three directions along the length, width, and depth direction. That is called as homogeneity. If all the elastic properties remain same, that is Young's modulus, Poisson's ratio, so whatever it is there, rigidity modulus, if they are same in all the three directions along the length, width, and the depth, then it is called as isotropic. That is the difference between physical properties are same, homogeneous, elastic properties are same, isotropic. Then second one, column is perfectly straight. That means it is not a bent column. So verticality is there for the column. It is perfectly straight. That is the second assumption. Third assumption, the axial or compressive load is collinear with the axis of the column. That's what I told yesterday. So the load acts exactly along the axis of the column. So this is the axis of the column. So if the load acts somewhere else at some distance from the axis, the distance is called as eccentricity, denoted by small e. So in that case, Euler's formula cannot be used. So Euler formula can be used only when the load is exactly coinciding with the axis of the column, compressive load. Fourth one, the self weight of the column is neglected. We are not considering the self weight. The column fails by buckling only. So that means it is a long column. It fails only by buckling, not by crushing. That is the meaning. The section of the column is uniform throughout. That means the cross section of the column remains same. There is no increase in diameter or decrease in diameter. It is not a tapered. Okay. So width or diameter, whatever it is there, for the entire length of the column, it remains same. Suppose if the column is like this. See, here you can see that it is a tapering column. So diameter, if it is a circular column, it is a tapering circular column where the diameter is increasing from top to bottom. In this case, we cannot use that Euler's formula. So it should be uniform throughout. Crippling stress is not greater than yield stress. So this is another thing. Yield stress means you have studied about the yield stress in the first chapter. Simple stress and strain, when we plot the graph of stress versus strain for mild steel, you have the stress, one point of stress, upper yield point and lower yield point. You have to recall that. So this crippling stress is, the assumption is, it is always less than the yield stress value. So these are the assumptions we are going to make for deriving the Euler's equation. Now all of you please observe here, very important derivation. So if you understand one derivation, all the other three derivations, of course, they run in the same lines. So there are 4 derivations, they can give any one of them. So only thing is the expression for moment is different in all the 4 derivations. So first standard derivation is when the both ends hinged. So here you can see that this is a column with both ends hinged. So hinge is shown like this. A and B, they are the hinge points. They are the ends of the column. Small l is the actual length of the column. See, small l is the actual length of the column. A and B are the hinged ends. Now, when the load P is applied like this, so you can see here, load P is applied, compressive load is P is applied, and this is the reaction. So due to this load, there develops a reaction here in the upward direction. Load is downwards here, reaction will be upwards, and the magnitude will be same. This is also P, this is also P. So this is the load, this is the reaction. Please note, the load is applied here at the end B. Now once the load is applied, when it starts buckling, it buckles like this. This is how it buckles. As we know, at the hinged end, you have deflection 0, but slope will be there. That means theta will be there. That is why it bends like this. It bends like this. This I have explained yesterday. So this is the buckling curve. You can call it as buckling curve. And what you have to do is you consider a section XX at a distance x from the bottom. So from the end A, you consider a section XX of this in this buckling, and the deflection at that lateral deflection, we call it as lateral deflection because it is horizontal. So deflection at that XX, I will take it as y, small y. See here, y is the lateral deflection at section XX, which is at a distance x from the bottom. So please note that x is measured from A to B. So x is equal to 0 at A and x is equal to L at B. Please note that. That is the, when you are using the boundary condition, you should be knowing the values of x. At A, x is equal to 0. At B, x is equal to L. And at any section XX, at a distance x from the end A, so lateral deflection is y. So this is what we wanted to say. Now this column behaves like a beam only. So the moment equation, deflection equation, or the curvature equation. Actually, this is not deflection equation. This is curvature equation. We can make that correction. The curvature equation we have derived in that deflection chapter, which is given by moment is equal to EI into d square by dx square. So same equation holds good here also, where mx is the moment at xx. So moment at this section xx is mx. EI is once again called as flexural rigidity. I have told about that in the deflection chapter. And d square by dx square is the curvature. Same thing, same notations are used. Only thing is to find this mx, please note that we have to use this sign convention. So this is important. Here the buckling is like this. Buckling, when the buckling is like this, we take the moment here as negative. Please note that. So that is the only thing you should remember. Moment is taken as negative if the buckling is like this. So that means here the deflection is y, P is the force. If you see to the left side of the section, if you see to the left side of the section, P is the force, y is the distance. That is the deflection where it is acting. So that means this P into y becomes the moment at this section XX. Please understand this, very, very important. So this P is acting at a distance y from this point. We have to take this point now. Section XX is considered here. Okay. So after buckling, I have to take the moment here. So moment here will be, if you see to the left side, so this of course this P is there, this y is there, but only thing is the sign convention is if the bending is like this, we take negative. If the bending is like this, we take positive. So this is a little bit opposite of that beam. So okay, so this is how the sign convention is used. So mx in this case it is negative because the buckling is like this. And what is that moment? P into y. So it is minus P into y. So mx is minus P into y. So that's what I wanted to tell. So this is the section xx where the deflection is y and the force is P. Force applied is P. This distance from here to here is x. So x is measured from A. So A is the origin. You can make a note there. Brackets you can write A is the origin. So that is x is equal to 0. At B, x is equal to L. Now the moment now is at xx it is minus P into y. Now in this equation you substitute that. So EI into d square by dx square is equal to minus Py, or you bring this minus Py this side. So and simplify. So, okay, so EI into d square by dx square plus Py is equal to 0. Divide throughout by EI. So you'll be getting d square by dx square plus P by EI into y is equal to 0. So this is the differential equation we are going to get after substituting for the moment. Now you have to remember the solution. You no need to solve this. There is a mathematics part, but you have to remember the solution. So the solution of this differential equation is given by this. So solution means after integrating these 2 times, and you know how to solve differential equations. You might have studied earlier, but you need not solve this equation. Remember this. That's why I have put star here. The solution you have to remember the solution of the second order differential equation. This is second order differential equation because d square y by dx square term is there. So it is given by y is equal to C1 cos x root of P by EI plus C2 sin x root of P by EI. So this you have to remember. Okay, you need not solve that. If you solve this equation, you are going to get this. Now there are 2 constants here, C1 and C2. So those 2 constants have to be evaluated using boundary conditions. So C1 and C2 are found out using boundary conditions. Now we know depending on the end conditions or the support conditions, we can write the boundary conditions. See here, at the end A, x is equal to 0, y is equal to 0 because there is no deflection at A. Similarly, at B, x is equal to L, y is equal to 0. So those 2 are the boundary conditions we have to use here. So let us use the first boundary condition. At x is equal to A, at the hinged end, y is equal to 0. So at x is equal to, at the point A, x is equal to 0, y is equal to 0. Put that here. And substitute in this equation. So LHS is 0. RHS becomes, see, this becomes cos 0. Cos 0 is 1. So C1 into 1 plus C2 into sin 0 is 0. It becomes 0. So from this you will get C1 as 0. So the value of C1 becomes 0. That means this term will vanish. Next, second boundary condition to find C2, it is at B. So at the other end, at the hinged end B, x is equal to L, but deflection is 0, y is equal to 0. So say these 2 you have to substitute here. So y is equal to 0 is equal to C1 we have proved that it is 0 here, plus C2 into sin of x becomes L here. X becomes L. So sin of L into root of P by EI. So that means you are getting 0 is equal to C2 into sin of L into root of P by EI. C2 cannot be 0. Why C2 cannot be 0? Since C1 is 0, if C2 is also 0, then y becomes 0 here. If you put both C1 and C2 as zeros, there is no deflection at all. So it is not correct. So it buckles. So therefore y will be there. So in order to say that y will be there, C2 cannot be 0. So therefore what is the other option? Sin of L into root of P by A should be 0. Now this is the equation we are going to get. Or you can write, what is the general solution of this? Sin theta is equal to 0 solution. So sin theta is equal to 0 solution is n pi. So theta is equal to plus or minus, theta is equal to n pi. So that is general solution. You have to remember that also here. Okay. General solution you have studied in trigonometry in your class 11 or class 12, PUC. So you have to remember that general solution of this is in the form sin theta is equal to 0. So if sin theta is equal to 0, general solution of that equation will be theta is equal to n pi. So here theta is nothing but L into root of P by EI, which is nothing but sin inverse of 0. Sin inverse of 0 will be is equal to n pi. So treat this as theta. Theta is equal to n pi is the general solution. Theta is this. So this is equal to n pi. where n is 0, 1, 2, 3. So that is n can be have any value of this. But what you have to do is you have to take only one solution among this. So that is the least non-zero integer. Least non-zero integer is 1 here. So take n is equal to 1. This is the general solution. Particular solution we have to take n is equal to 1. So if you put n is equal to 1, so then L into root of here P becomes PCR now. Please note that P becomes PCR. That is the crippling load. So when n is equal to 1, we take P as PCR. So root of PCR by A is equal to n is equal to 1 means it becomes pi. Now square both sides and simplify. So you will get PCR as pi square EI by L square. So this is the formula we have to use to find the crippling load. So PCR is called as the crippling load, Euler's crippling load. This formula is called as Euler's formula. So if you know the value of E, I and L, L is the actual length of the column. Please note that L is the actual length of the column. E into I is called as the flexural rigidity. Flexural rigidity. So PCR is equal to pi square EI by L square. So this is the formula we have to use to find the Euler's crippling load when both the ends of the column are hinged. So that is very important. So when the condition is both the ends of the column are hinged like this, then the formula to find PCR, crippling load of the column, is pi square EI by L square. Now, this is one formula. Now, let us take the second condition where Euler's formula for a long column with one end fixed and other end free. So, the figure will be like this. So, this is fixed end. So, fixed end is A, free end is B. There is no support here. So, load P is acting like this. So the deflection will be like this. It's like a cantilever. You can see here. So if you take a section x, xx here at a distance x, from the fixed end here. So x is equal to 0 here. Please note that x is equal to 0 at A, x is equal to L at B. Same thing. So this is called as the axis of buckling. So the column buckles like this. Xx I am going to take here. This distance is x. Now I have to take the moment here. Please note that same procedure we are using. Mx is the moment here. If you want the moment here, what you have to do is see to the right side. So this side. So from this section, you see to the right side. P is the load, and what is the deflection here? What is the deflection here? It is A minus phi. Please note that this P will be acting at a distance A minus y. So this you remember this. So in this case it is mx is P into A minus y. So this is y. If you draw a ordinate here, so this P will be transferred over here. So this P will be multiplied by A minus y, this distance, because this section is here. See here. So this is where you have to take the distance. So this is y. From here to here it is y. Total is A here. At the free end deflection is A. So that difference A minus y, we have to multiply that by P. So this P is transferred over here. Please take that P here. P will be here. So that P into, once it's initially P will be acting here. Once the buckling starts, P will go here. So this P into A minus y is the moment. That is very important. There it is minus Py. Here it is plus P into A minus y. This is plus because the buckling is like this. So in the last derivation I have told. So depending on the, see here. So if the buckling is like this, moment is negative. If the buckling is like this, like a cantilever, buckling, this moment is positive. So just opposite of the beam. Yes. Now that means in this case, mx. So same thing. All these remain the same notations. L is the actual length of the column. A is the lateral deflection at B. B means that is the free end. P is the compressive load. PCR is the crippling load. Consider a section XX at a distance x from the point A. So Y is the lateral deflection at XX. Same thing. Same notations. But only thing is moment will be at XX. Mx will be P into A minus y positive because the buckling takes like this. So Mx is equal to P into A minus y. See here. And use that curvature equation. Mx is equal to E into du square by dx square. So mx is p into a minus y. Therefore, equating these two. So ei into d square by x square is equal to p into a minus y. So how it is p into a minus y? I have shown here. See here. This is p. This distance from this xx, this distance is a minus y. So that is why this is the moment. Now simplify this. So bring this to this side. So ei, you will get this equation. So all this you have to do. Write down all this in your notes so that it will be easy for you to. So derivation, any one of these four derivations may be asked. Procedure is same. Only this mx term will be different. Figure will be different. But figure you have to show the boundary conditions, support conditions, everything for the given thing. Then this moment expression is different. Then solution will be different. So see here in this case, the solution of this differential equation is this. You can add here solution of this differential equation is this. Whereas in the last case, it was only these two terms. But here one more will be added, plus a will be added. So I hope you remember when you are solving differential equations, you'll be having two terms. One is the complementary function and the particular integral. So two parts will be there. So like that. So that is why you need not solve this. Just remember the solution. So whatever is there in brackets, it is same. See here, c1 into cos of x into root of p by ei plus c2 into sin of x into root of p by ei plus a is extra here because of this. In the last derivation, RHS was 0. When both the ends are hinged, see here, RHS was 0. That's why you had only these two terms. Plus term is not there. Whereas here, so this is called as complementary function and this particular integral here is 0. But in the second case, particular integral is a here, small a. So that you should remember. So once you write this solution of this differential equation, once again C1 and C2 are found out by using boundary conditions. Now here, what are the boundary conditions? See here, the boundary conditions in this case are at end A, x is equal to 0, y is equal to 0. And at also at end A, x is equal to 0, dy by dx is also 0 because it is fixed end. So you know that at the fixed end, both slope and deflection are zeros. So the boundary conditions are now at B you don't have anything 0. So both slope take that as boundary condition. So at A, x is equal to 0, y is equal to 0, that is deflection is 0. And also at A, x is equal to 0, dy by dx is equal to 0, that is slope is 0, is 0, theta is dy by dx. Now if you use those two equations, see here at fixed end A, slope dy by dx is equal to 0 and deflection y is equal to 0. So if you want to use that, this boundary condition dy by dx is equal to 0, you have to differentiate this. Because y is this, dy by dx, differentiate 1, this is 1 with respect to x if you do. So if you differentiate this, you will get this. So differentiation of cos theta is minus sin theta, you know that. So minus c1 sin of x into root of p by ei into root of p by ei you will get. So that is using the chain rule. Then differentiation of this will be c2 into cos of x into root of p by ei into root of p by ei, and the derivative of this will be 0 because a is a constant. So dy by dx will be this. Now apply. First I will apply this. At x is equal to 0, dy by dx is 0. If you apply that to this, so what happens? You can call this as equation 2. The LHS becomes 0 now, is equal to, since x is equal to 0, sin 0 becomes 0. So first term becomes 0. Second term becomes cos 0 is 1. So C2 into root of p by ei. So C2 into 1 into root of p by ei. So since LHS is 0, C2 becomes 0 here. So please note that. So this value of C2 becomes 0 here. Now use the second boundary condition. Second boundary condition is at x is equal to 0, deflection is 0. That is y is equal to 0. If you substitute that in this equation, deflection equation, in this equation, so at x is equal to 0 means this becomes cos 0. Cos 0 is 1. So it becomes 0 is equal to c1 into 1 plus c2 into 0. Because x is 0, sin 0 is 0 plus a. So a will be there. So if you simplify that, you will get c1 as minus a. So observe, by applying the boundary conditions, you got the value of c2 as 0 and c1 as minus a. Now substitute these two things here in this. So y is equal to what you will get? So y is equal to, you will be getting, since C1 is 0, this term will not be there. C2 is minus a, So then it becomes minus a into sine of x into root of p by ei plus a. Like that you will get. Okay. So that is what you are going to get. See here. This is what you are going to get for y. Now, one more boundary condition we will use here to get the final crippling load term. So at end B, that is at x is equal to L. So at end B, x is measured from A, So here at end B, x is equal to L. At x is equal to L, y is equal to A here. So that is the maximum deflection. So y is equal to A there. So you have to use that condition here for this equation. So you have got this equation now. In this, you apply one more boundary condition, that is at end B, x is equal to L, y is equal to A. So put y is equal to A here. So A is equal to A into 1 minus cos of, instead of x you take L, root of p by A. Now this A and A will get cancelled. So in the LHS you will get 1 here. So 1 is equal to 1 minus, so like that you will get 1 is equal to 1 minus cos of L into root of p by ei. So this 1 and 1 also will get cancelled. So you will be getting cos of L into root of p by a as 0. Because this 1, if you bring to this side, or if you bring this cos to this side, it becomes plus. This 1 you bring to LHS, it becomes minus 1. So 1 minus 1 becomes 0. So now what is the general solution of this one now? So general solution of cos theta is equal to 0 is theta is equal to n pi by 2. So you should remember that is a trigonometrical solution. So general solution of cos theta is equal to 0 is n pi by 2. Theta is equal to n pi by 2. Now this is theta now. L into root of p by e is theta. So this is equal to n pi by 2, where n is 1357. Please note that n is an odd integer here. So this you should remember. The general solution you should remember. Now once again, consider the least non-zero value of n. Least non-zero value of n is 1 here. N is equal to 1. So when n is equal to 1, this p becomes PCR. So put n is equal to 1 and p is equal to PCR in this. So what you will get? L into root of PCR by ei is equal to, n is 1 here. So 1 into pi by 2 means pi by 2. Now square both sides. L square into PCR by ei is equal to pi square by 4. It becomes pi square by 4, or PCR is pi square ei by 4 L square. So this is the Euler's crippling load when one end is fixed, another end is free. So let us see what is the difference between this and the earlier one. So first derivation we did for both ends hinged. In the case of both ends hinged, the formula was pi square ei by L square. Whereas in the case of one end fixed and one end hinge, it is pi square ei by 4L square. There it was L square. Here in the denominator we are getting 4L square. So if you compare this and that, PCR of that is more, because here in the denominator we have 4L square. There in the denominator we have only L square. That means if you compare this PCR and that value of PCR, for the same value of L, for the same value of E and I, so that column, that is when both the ends are hinged, it will take more load than this column. That is more stronger, because this value is less. How much time it is less? 4 times it is less. So if you take that one as PCR1, this one as PCR2, you can see that PCR1 is 4 times PCR2, or PCR2 is 1 by 4 times PCR1. So if you take 1 by 4 outside here, you will be getting pi square ei by L square only. Pi square ei by L square is that the value you got for both ends hinged. Okay, so that is why I have written one sentence here. Note, for the same length of the column, so L remains same, the cross section and the material being the same. So material being the same, cross section being the same means I remains same. Material being same means E remains same. A column with both ends hinged can carry a load which is 4 times higher than the load carried by a column with one end fixed and other end free. So This is actually 1/4 of what you got for that both ends hinged case. So in other words, what you can say, if a column, if you compare two columns, one column, both the columns have same length, they have same E value, they have same I value. Okay, E, I, and L are same. Only change is in boundary condition. That is, in the first column, both the ends are hinged. In the second column, bottom end is fixed, top end is free. So if you compare the load carrying capacity strength of those two columns, the first column can take 4 times more than the load than the second column. So both ends hinged is 4 times stronger than one end fixed and one end free. This is what I wanted to explain you today. So two derivations I have explained you today. So in the next class, I will take another two derivations are done in the same this thing continuation. Euler's formula for long column with both ends fixed. See, in this case, both ends fixed case, the buckling will be like this. The buckling will be like this here. Because we know that at the fixed end, rotation is 0, that is slope is 0, as well as deflection is 0. So that is the boundary condition. And in this case, what happens to the mx? Mx is the procedure remains same here. So mx in this case is m minus py. So why it is m minus py? I will tell you. So when you take the left side of this xx, that means downside of this xx, there develops a moment here because of the fixity condition. There develops a moment here. So that here also it develops a moment because both ends are fixed here. So fixity means there will be a reaction moment. So that reaction moment will be like this. So this minus py we had to take. So that's all. So m minus py is the moment expression there, mx. That's all the difference. Then you equate that ei into d square by dx square to that m minus py, and this is the curvature equation you are going to get. So this is the curvature equation, and this is the solution of that equation. So this you should remember. That's what I told. You need not you cannot solve this. It's a mathematical part. Don't worry about that. Write this equation. So you have to remember this mx expression. Then this equation you are going to get. Write the solution of this equation. Directly you can. Solution of the above differential equation is this. So here also you can see first two terms are same as in the earlier case. Only second term will be m by p here. So in the first case, this second term was not there. Second case, it was small a. Third case, it is m by p. So first two terms are same. So for this, you calculate dy by dx also. Differentiate this with respect to x, you will get dy by dx. So here, once again, C1 and C2 are evaluated using boundary conditions. What are the boundary conditions we are going to use here? At the end a. At the end a, we know that x is equal to 0, y is equal to 0, as well as dy by dx is also 0. Because it is fixed condition. The only addition thing is there develops a moment here because of fixity. So at fixed end a, dy by dx is 0. So at x is equal to 0, dy by dx is 0. That is slope is 0. If you use that here in this equation 2, 1 and 2, in the equation 2, if you use this boundary condition, so LHS becomes 0. So you will be getting C2 as 0. Says then in the first equation, at the fixed end a, that is at x is equal to 0, y is equal to 0. If you use that, then if you substitute in this equation 1 and simplify, you will get the value of C2 there. So C1 will be minus m by p. So once you get C1 and C2 values, substitute that in the general expression here. So C1 now you got, C2 also now you got, substitute in this. So then you will get the deflection at any point. General equation you are going to get like this, m by p into this. Now you apply the third boundary condition, just what we did in the last derivation. At b, that is the upper end, x is equal to l and y is equal to 0. If you use that here, then you are going to get something like this. So if you substitute for x is equal to l, y is equal to 0, you are going to get an equation like this. Here m by p cannot be 0. Therefore, the condition is this will be 0. When you take that as 0, so the general solution becomes now cos of L into root of P by A is equal to 1. So cos theta is equal to 1. General solution is this, n pi. So theta is here, L into root of P by A. So theta, cos theta is equal to 1. That is the equation here we are going to get. General solution of cos theta is equal to 1 is theta is equal to n pi, where n is odd number, even integer. Okay. So once again 0, 2, 4, 6 like that. Once again you take first least non-zero. Least non-zero is 2 here. 2 here. After 0 you have to take 2 here. So if you take least non-zero integer for the n, if you put n is equal to 2, p becomes PCR here. Now substitute in this, L into root of PCR by A is equal to 2 pi. N is equal to 2. So if you simplify this one, you see you are going to get PCR is equal to 4 pi square EI by L square. 4 pi square EI by L square. See the difference. In the first case, both ends hinged. It was pi square EI by L square. In the second case, one end fixed and another end free. It was pi square EI by 4L square. In the denominator 4 was there. In the third case, when both the ends are fixed, you are getting 4 pi square EI by L square. So if you compare these three formula, what you can say here is, this both ends fixed is there, it has got the highest strength, because this is 4 times more than both ends hinged. See here, both ends hinged is 4 times stronger than one end fixed and one end free. And both ends fixed is 4 times stronger than both ends hinged. That means what you can say, this both ends fixed condition, it is 16 times, 4 into 4. 16 times stronger than one end fixed and one end free. So this is what we can say. That means a column which has got both ends fixed, they are more stronger than other conditions. So this fourth one we'll discuss in the next class. So what I wanted to tell you is, today I have discussed about 3 derivations. All the 3 are Euler's equation only, but based on different end conditions. Both ends hinged, one end fixed and one end free, both ends fixed. So we have calculated the Euler's buckling load. So when the column buckles, that is the minimum load before the buckling starts in a column or a long column. Only difference is here, please note that the expression for mx, bending moment expression, is different. Then you have to, that solution y is equal to whatever you get. So that you should remember. Mx you have to remember. Y equation you have to remember. Then boundary conditions. So if you know these 3 things, you can derive this equation easily. So this is what I wanted to tell you today. So practice these 3 derivations today. So tomorrow or in the next class, I am going to discuss about that 4th one. Then after that, we have to use one more equation called Rankine's equation. Then some problems on Euler's and Rankine's equations. If I do that, then this chapter will be over. Okay. So comparison, everything I have given here. Anyway, I will explain this once again. These 3 derivations you try to practice. Then we will go for Rankine's formula. Then problems. So I think I have given some 8 to 10 problems this chapter. 7, 8 to 10 problems I have solved. I think if you understand those problems clearly, that is more than enough. So that completes the 5th module. So practice these 3 Euler's equation. Write down the sketch. Write down the expression for mx. Buckling curve you write. Then distance x is measured from the what point, you show that in the diagram. Then mx expression you write. Then use that mx is equal to EA into d square over dx square curvature equation. Substitute for mx. Then you will get the differential equation, second order differential equation. Remember the solution for that, y is equal to, then if you want you can derive the derivative of that dy by dx. Then find out the constants of integration C1 and C2 by using the boundary conditions. So boundary conditions should be careful. At the hinged end, slope is 0, slope is not 0, deflection is 0. At the fixed end, both are 0. Deflection as well as slope is 0. At free end, both are not 0. So deflection is not 0, slope is also not 0. So depending on the boundary conditions, you can get the different expressions for Euler's buckling load, and I have compared that also. So I want you to practice these things. and be thorough. One of the derivations may appear in the examination. If they don't give derivation, definitely they will give problem. So this is what I wanted to explain you today. Practice it. Once you start practicing, then only you will understand. Otherwise, it will be difficult. Only 5 students are there today. Okay, 19005. 006.
Sir, 3 then.
006.
Present, sir.
7.
Present, sir.
18. 18.
Sir, 16
19.
ಇತ್ತು.
16.
ಹಾ
16
ಸರ್,
ಕಾಣಿಸ್ತಾ
ಅವಳು
ಇಲ್ವಲ್ಲ ಇಲ್ಲಿ?
ನೆಟ್ವರ್ಕ್
Sir,
ಇಲ್ಲ
005
ಸರ್, ಅವಳು
present.
ಕಟ್ ಆಯ್ತು.
Sir, 002.
002 ನಾ?
2, sir.
5.
002 ಇಲ್ಲಿ ಕಾಣಿಸ್ತಾ ಇಲ್ಲ.
Sir,
Not
14
visible.
members ಇದ್ದಾರೆ ಸರ್.
Sir,
ಇಂದ ಬರೀ 7
005.
posts ಇದೆ.
14
Sir,
ನಂಬರ್ ಇದ್ದೀರಾ?
17.
ಹ್ಞೂ ಸರ್.
ಇಲ್ಲಿ ಓನ್ಲಿ 5 ತೋರಿಸ್ತಾ ಇದೆ.
40 members ಇದ್ದಾರೆ ಸರ್ ಆದ್ರೆ.
It is
ನಿಮ್ದ್ರಲ್ಲಿ ಬರೀ 7
5.
posts ಇದೆ ನೋಡಿ ಸರ್. 14 members ಇದ್ದಾರೆ.
We'll,
7 ಅಲ್ಲಿ ನಂದೇ 2.
put it in the
ಆಯ್ತಾ?
chat if you want.
ಇನ್ನು
ಸರ್
5
ಆದ್ರೆ
ಜನ
12 members ಇದ್ದಾರೆ ಸರ್ ನಿಮ್ಮನ್ ಬಿಟ್ಟು.
ಯಾರು ಬರ ಯಾರ್ಯಾರು ಹೇಳಿ?
Sir,
Number ಹೇಳಿ.
013.
ಸರ್
ಯಾರು
0
ಒಬ್ರು ಹೇಳಿ. ಒಬ್ರು ಹೇಳಿ.
ಸರ್
ನಂಬರ್
002.
Sir, 012.
016 ಆಯ್ತು. ಓಕೆ,
Sir, 018.
ಆಯ್ತು.
017.
005.
ಒಬ್ರು ಹೇಳಿ, ಯಾರಾದ್ರೂ ಕನ್ಫ್ಯೂಸ್ ಆಗ್ತದೆ.
003.
003. ಓಕೆ.
ಸರ್ 002.
005.
5 ಇದೆ. 5 ಕಾಣಿಸ್ತಾ ಇದೆ ಇಲ್ಲಿ. ಓಕೆ.
002.
Sir, CV 012.
2. ಓಕೆ, ದೆನ್
007.
012.
ನೋಡಿ ಹೇಳ್ತಾ ಬರ್ತೀನಿ. 2 3 5 6 7 16 18 19. ಇನ್ಯಾರಿದ್ದಾರೆ?
Sir,
17.
013. Sir, 012.
Sir 21.
21.
Sir, 028.
ಇನ್ನೊಬ್ಬ 9 ಜನ ಆಯ್ತಲ್ಲ.
Sir, CV 012, sir, 12. Sir, 013 also.
ನಿತೇಶ್.
Yes, sir. Sir, Rahul also present, sir.
ನಂಬರ್ ಎಷ್ಟು?
Sir, Tejas present, sir.
Sir, 12, sir. Rahul 12.
ಟೋಲ್ ಬರ್ತಿದ್ದೀನಿ. ಓಕೆ. ತೇಜಸ್ ಎಷ್ಟು? ನಂಬರ್ ಎಷ್ಟು? ತೇಜಸ್ ನಂಬರ್ ಎಷ್ಟು?
CV 028. CV 028, sir.
18 ಅಲ್ವಾ ನೀವು?
Yes, sir.
ಸರಿ. ಓಕೆ.
Sir, 017.
ಆಯ್ತು. 0 ಕೊಟ್ಟಿದ್ದೀನಿ. ಯಾಕೆ ಇಲ್ಲಿ ಕಾಣೋದಿಲ್ಲಲ್ಲ ನಂಬರ್?
ಸರ್ ನಿಮ್ದು ನೆಟ್ವರ್ಕ್ ಪ್ರಾಬ್ಲಮ್ ಇದೆ ಸರ್.
13 ಜನ ಇದ್ದಾರೆ. ಓಕೆ, ಆಯ್ತು. ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡಿ. ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್.